transportation landscape, advancement in power electronics are crucial for enhancing efficiency, performance, and sustainability. This FDP will provide the fundamental principles, recent developments, and emerging trends in wide bandgap semiconductors, focusing on their impact on electric powertrains, charging infrastructure, thermal management, and system level optimization. We wishing you all an insightful and engaging FTP. May I request all the participants to turn on your cameras for an official snap. I request the participant to turn on your cameras for the official snap. Thank you, participants. Now, I would like to welcome Dr. B. Vinod Kumar, coordinator of the ATAL FTP program and program coordinator of Department of Electrical and Electronics Engineering of Dr. Mahalingam College of Engineering Technology, to welcome the gathering. Sir, please.
Thank you, Mr. Tony. So good evening, everyone. It is my immense pleasure to welcome you all to the ATAL Online Faculty Development Program on revolutionary electric powertrains, the role of wide-bandgap semiconductor in overcoming the challenges and shaping the future trends.
Coffee.
So we are excited to see the gathering of 285 participants from various esteemed colleges and universities across the country. Vehicles and the technology driving the future. So first, I would like to extend the warm welcome to our chief guest, Dr. Senthilkumar, Professor, Department of EEE, NIT Trichy. Welcome you, sir. I'm going to extend a warm welcome to our principal as well as vice principal, Dr. Senthilkumar, our dean R&I, Dr. Ramakrishnan, our academic associate dean, Dr. Vijay Kumar, and our beloved head of the department, Dr. Ganesh Kumar, and our professors, senior professors from our department, Dr. Kalim Murthy, and the entire faculty team, and my coordinator, Dr. Venkatesh. Your continuous supports and encouragement plays a crucial role in organizing such a meaningful event. So a special note of gratitude goes to the ATAL Academy, Government of India, for their generous financial support, which has made this FDP possible. The initiative of ATAL Academy to foster excellence in higher education through training and development of the faculty members has made a significant impact across the country, and we are privileged to be a part of it. To all the participants, we thank you for your eagerness and commitment to expanding your knowledge. Over the next few days, we have an exciting lineup of sessions where we will explore the revolutionary role of wide-bandgap semiconductors in the EV industry. So we encourage you to actively participate, ask questions, and engage with experts and the peer alike to enrich your learning experience. So we are certain that the insights shared here will not only enhance your academic expertise, but also will help to shape the future of the electric vehicles. We're contributing to more to sustainable and the technologically advanced world. So once again, I welcome you all to this FDP and thank you for being a part of this valuable learning opportunity. I wish you all a rewarding and insightful experience. Hey, thank you all.
Thank you, sir, for your welcome address. Now, I would like to request Dr. D. Ganesh Kumar, sir, head of the Department EEE, to address the gathering. Sir, please.
Good evening, all. I joined with Dr. B. Vinod Kumar, in welcoming all the participants across the country, and also a special welcome to today's expert, Dr. Senthilkumar from NIT. It is a career-oriented, technology-oriented, knowledge-fulfilling journey for all the technocrats in India. After this ATAL mission, many workshops, many faculty development programs are being organized under different sectors for training ourselves to compete the world tradeful knowledge. Nowadays, across the country, many FTEs are being run from Dr. Mahalingam College of Engineering and Technology, Pollachi in the part of Tamil Nadu. We are organizing this 6-day ATAL FTP program on revolutionizing electric vehicle powertrains, the role of wide-bandgap semiconductors in overcoming challenges and shaping the future trends. Semiconductor industry is being driven now to fulfill the requirements from all the sectors of technology. In fact, the multidisciplinary nature in the technological demands the mechanical engineering knowledge, electrical engineering knowledge, electronic engineering knowledge, same of all the software clustering knowledge. It is an insisting trend to learn ourselves or enriching our knowledge in this sector. I appreciate the organizers, Dr. G. Vinod Kumar, Mr. A. Venkatesh, and the organizing members, Mr. R. Muthu Bharati, Dr. G. Anand Kumar, Mr. Sam Suresh, and Hubert Tony Raj. We have invited experts from NITs, IITs, and a few foreign experts for this FTP. And all these experts are well known in their field. So, my dear participants, I request every one of you to interact better during these sessions, and also this FTP will definitely enrich your knowledge and also wisdom across these e-vehicles. Everywhere here and then, different competitions, hackathons, technologies across the country are being driven on this e-vehicle. We have taken the micro level and also the completely serving sector, the semiconductor industry. Knowledge towards the requirement on the e-vehicles from the semiconductor industries. As we know, as the semiconductor industry is growing, our computer speed is getting increased. From the Pentium series to the recent I series, the bandgap gap is giving the very fulfilling trend in the semiconductor speed. So like that, each field is demanding the semiconductor technology to drive the field better. So the knowledge in this FTP will give you the semiconductor industry-based requirement on vehicle. I appreciate all the organizers. I personally thank all the experts who have given for delivering, for sharing their knowledge in this FTP. All the very best to all the participants, and thank you for the organizers.
Thank you very much, sir, for your addressing. May I request Dr. A. Senthilkumar, sir, Vice Principal and Professor of Dr. Mahalingam College of Engineering Technology, for the presidential address. Sir, please.
Good evening, everyone. Indeed, it is a pleasure to join with you all. Actually, this topic is the order of the day. Everybody is talking electric vehicle, and our coordinators specifically selected this topic, focusing on wide-bandgap devices. So actually, as Dr. Ganesh Kumar mentioned, this is an interdisciplinary subject. It contains everything, software, hardware, AI, So entire world is focusing on that. So we are also need to focus on that. Actually, this 5 days is not enough to cover entire spectrum of working area. So as this our team is very strong in power electronics segment, they are trying to cover the wide bandgap semiconductor in the electric vehicle. Hopefully, the next few seminars will cover the remaining area as well. So first, I thank all the participants who are interested in participating in this. I think around 285 participants are interested to join in ATAL FTP. So, and also ATAL is doing very good work across the world. They are performing well. They are educating, developing the skill across the engineering faculty in a very good way. So we have to congratulate ATAL for this their effort. And also, I joined with Dr. Ganesh Kumar to congratulate the coordinating team, Dr. Vinod Kumar, Mr. Venkatesh, Muthu Bharati, Anand Kumar, Sham Suresh, and Tony Raj. So I request all the participants to interact, and actually the resource person we have arranged is really the worthy, So you have to interact and get out of that. So with this, I wish all the participants and coordinators for the good success. Thank you. Thank you very much.
Thank you very much, sir. Now, it's time to introduce our chief guest. Our chief guest is Dr. S. Senthilkumar. Did his UG in Electrical Electronics Engineering, Tyagaraja College of Engineering, Madurai. Did his PG in Electric Drives and Control at the Pondicherry Engineering College, Puducherry. He did his PhD at the National Institute of Technology, Tiruchirappalli. His area of interest falls on electric machines drives, energy conversion, microdrift, power quality, power electronic interface for enabled energy system, and analog and digital controllers for power electronics. He has over 23 years of teaching experience in various engineering colleges. His footstep in NIT Trichy started from the year of 2006 to the present. He has published over 46 XAI and Scopus journals that includes notable publications in IEEE Transition and Plasma Science, IEEE Transition in Electron Device, IEEE Transition in Electrical Energy Systems, IEEE Transition on Power Electronics, and furthermore, journals like Elsewhere, Wiley, and Taylor and Francis. He has published over 31 international conferences and national conferences that includes the major publication on IEEE index conferences. He has supervised over 27 UG scholars, 93 MTech scholars, and he has guided over 10 PhD scholars in his experience in IT. He has successfully completed sponsored projects from DST, CERD, ISRO, MIT, NLC, MHRD, and funding from CDAC. Over on his accomplishment, he has acquired over 5.2 crores net from the different agencies. He has contributed to the institution as academic and administration part as TechCube Nodal Officer and Associate Dean of Electrical. Sir is currently serving as Professor in Department of EEE at NIT Trichy. Now, I request Dr. S. Senthilkumar Sir for the inaugural address. Sir, please.
Good evening, all. First of all, I congratulate the management, principal, coordinators.
Sir, good evening, sir. You are audible, sir.
Yes, thank you, sir. First, good evening, everyone. First of all, I congratulate the management, principal, coordinators for conducting such a wonderful faculty development program in the field of wide bandgap devices The application chosen is electric vehicle application. First of all, I just want to tell you here, nowadays the wide band gap devices are famous for many applications. So one of the application is the electric vehicle application. So with the introduction of the new wide band gap materials, such as gallium nitrate in transistor fabrication, significant figure of merit improvements translates into potential improvements in power supplies. So using newer materials that exhibit a higher band gap, that silicon-based semiconductors enables a reduction in die size while maintaining the same blocking voltage. A smaller die results in lower parasitic capacitance and lowering of both transistor gate charge and output capacitance. So this translates directly into faster transition speeds with less transition losses. So less loss dissipation, I mean the less driving losses at a given frequency compared to the state of art devices like classical. Sir, can you hear me?
Participant kindly mute yourself. Yes, sir, you can hear me, sir. Participant kindly mute yourself.
Sir, it's audible, sir.
Yes, thank you. So the designers don't drive the silicon FET in power electronic applications a few hundred kilohertz because of the switching loss. Because sir, can you hear me?
It's audible, sir. It's audible.
Okay.
Yes.
So
Sir,
when you
audible,
are
sir,
referring,
audible, sir.
yes.
But-
When you
But
are
some
referring the
disturbance is there,
designers,
sir.
when you are referring the designers don't have the silicon FETs in power electronic applications above a few hundred kilohertz become because the switching loss become prohibitively large. So the lower parasitics enable GaN-based FETs to operate at frequencies up to 10 times higher while maintaining comparable switching and driving losses. So this ability to operate higher frequencies, lower ripple voltage and current, which equates to lower conduction and magnetic core losses and potential reduction in size of the inductive and capacitive components. So in this regard, we are moving towards the high frequency operation. With higher frequencies, the need to store energy in between charging cycles is linearly reduced. Therefore, all passive components used for energy storage or filtering can be smaller. So size reduction benefits are especially evident in applications where size, weight, and form factor are critical. For instance, any application that is not stationary, such as for airborne or mobile systems, size and weight are major concerns as more fuel needed as a fuel is needed as weight is increases. The second advantage of shifting to high frequency operation for the power electronic devices is the reduction of the EMI filter. Passive filter becomes more efficient at higher frequencies and above 5 megahertz. The switching losses generated imposed by the standards. For example, the standards EN 55022 relaxes by an extra 5 dB. Higher frequencies are more likely to find a radiation path. However, the Faraday's shielding available only on the ground systems, and careful layout becomes increasingly important. So reducing component size as the frequency is increases, voltage and the current ripple is decreases, thus reducing the required capacitance. So large aluminum capacitors which are very effective up to the lower hundreds of kilohertz become ineffective once switching frequencies push to the megahertz realm. So you can replace aluminum capacitors with compact ceramic capacitors, which exhibit lower impedances due to both the structure and the connection method to the board. So using ceramic capacitors require that you pay attention to their self-resonance. So, and DC voltage biases. To counter these effects, select and carefully lay out lower impedance of form factors and select high-grade dielectric materials. So, similarly, you can reduce the size of the inductors or transformers, which increasing the frequency, but selection of the magnetic material that can maintain good performance at multiple megahertz with high changes in magnetic flux, that is d phi by dt, due to the fast changing currents is limited. So above 5 megahertz, it is possible to get rid of the solid core and adopt air core inductors. Air core inductors remove core losses but lower permittivity of air forces. Larger number of the turns for a given inductance value. This results higher copper loss and construction that might be lower in volume. That solid core solution with a strong field radiation out further into space. So the researchers are experimenting with a higher frequency magnetic material that might be a good solution for multi-megahertz application. According to this FDP, the organizers were chosen with the wide band gap devices for the power electronic applications. So particularly the electric vehicle applications. So I hope that the researchers will bring the good design by employing this wide band gap devices with respect to the applications like electric vehicle applications. So I hope this FDP will be fruitful and the participants will learn more information at the end of the FDP. So the journey of 1,000 miles starts with a single step. I hope this workshop will give the fruitful information about the wideband gap devices with respect to the applications like electric vehicle applications. Thank you.
Thank you very much, sir. It's time to thank. Now, I request Mr. A. Venkatesh, co-coordinator of the ATAL FTP program, assistant professor of Dr. Mahaling College of Engineering Technology, to deliver the vote of thanks. Sir, please.
Good evening, all. It's my pleasure to deliver the vote of thanks. First of all, I would like to thank the management, principal, vice principal, sir, all deans, my HOD, sir, and my coordinator, sir. And I want to especially thank one person, Dr. M. Kalimurthy, sir, for suggesting us to choose this topic for this ATAL FPP. Thank you, sir. And I would like to thank ATAL for providing us an opportunity to host this program. We expect a lot from the participants and from the resource persons. Let this FPP be an interactive one. Thank you all. Thank you all for participating. I would like to give the session to Senthil sir to proceed further. Just 5 minutes, participants. We can have the presentation view and we can start the presentation. Thank you all.
Now we formally close this inaugural function. Thank you very much, dignitaries, for being with us. And by we shall take 5 more minutes, and I request Dr. Senthilkumar, you can handle the section after 5 minutes, sir.
Sir, can you see my screen?
Yes, sir. It is visible. Visible.
Yes, sir. Visible, sir. It is clearly visible, sir. Now it is in the presentation mode, sir. It is clearly
Yes,
visible, sir.
yes. Okay, sir. Thank you, sir.
Now it's time for the first session. I would like to request Dr. S. Senthilkumar, Department of EEE of NIT Trichy, to address the gathering. Sir, it's all yours, sir. You may take the. Thank you, sir.
Thank you, Sir. Thank you for the introduction. Uh, during my inaugural address, I told you the wide band gap devices, semiconductor devices, it is famous for high frequency applications. I told you very clearly why we are going for the high frequency operation. We want to minimize the size and weight. So the applications, any applications wherever we are using the power electronics, we can take it to the wide band gap devices. That may not be the issue. So very recently we have awarded one of the project from MIT. It is about to complete that project based on the wide band gap devices. We were developed one welding power source. The power rating of the welding power source is a 6 kilowatt, but the current rating is a 200 amperes, 12 volt. So in this regard, we have chosen with wide band gap devices, and we have developed, and we observe that compared to the state-of-art welding machine with respect to the same rating, like a 200 amperes. So here we are, that indicates with about 120 kg, whereas by employing wide band gap devices, we brought it with about 50 kg. This is for your information. Okay, so now we will come to our topic. Actually, here I just want to discuss about the overview of the wideband semiconductor devices for power electronic applications. So here I just want to discuss. So why we need to go with the wideband gap devices. So and a model for the power semiconductor devices, and what are the wideband gap devices which is available, and how it will be the structure of the devices like a diode, transistor, how it will be the MOSFET, because the most of the applications we are using, and I just want to highlight some applications like electric vehicle applications where we are using, and motor drive applications, how we are using, then even like renewable energy applications, how we are using. So I just want to cover these things. And first, I just want to come here with respect to the wide band gap devices. So we need to understand how about the semiconductor devices. So I told you very clearly, the advancements towards an energy adequate world lies in the use of innovative materials such as wide band gap semiconductors. So the energy consumption and energy management of buildings mainly depends upon the power electronic converters and monitoring indoor conditions. Remarkably, more than 60% of energy utilized for electricity reproduction is lost during the conversion process. A majority of allocation of generated electricity is used only after a series of transformers that are highly inefficient and are carried out by the power electronic converters. So semiconductors are the basis towards development of numerous key technologies such as electronics, optoelectronics, communications, computing, sensing. The efficiency of the power electronic converters are based on the selection of the semiconductor devices and the switching frequency. So in power electronic converter system, the semiconductor devices considerably contribute to the power losses which can be associated with the conducting and switching currents. So the WBG devices, semiconductor material, should operate at a higher frequency to reduce the switching losses and to increase the power density of the converters. So therefore, the innovations in the power electronics becomes essential to cut down the power losses occurring during the power conversion process. In such a situation, utilization of the WBG semiconductor devices can allow expanding the electrical energy conversion ability along with the extraordinary progress in scope and vigor of power converters. So in this regard, one can understand that the device made from WBG material can reduce the power electronic component size, likely cut down systems of our component level costs while bettering their performance and reliability. So for this reason only, we are moving towards a WBG device. So here you can see that simply the increasing the energy with respect to the metal, how it will be, the semiconductor, how it will be, the energy gap, so how it will be. So the band gap indicates, dictates the energy required for electrons to move from the valence band to the conduction. So the band gap is the difference between the valence band to conduction band. Valence band represents the highest occupied state and the conduction band represents the lowest occupied state. So here the mechanism, how it is operates. So the band of electrons are orbits from vehicle, orbits from which electrons jump when excited. So the conduction band to which the electrons can jump. So here the electron, the band gap dictates the energy required for the electrons move from valence band to conduction band. Legacy silicon, which has been the primary material for the semiconductors in 1950s, has the band gap of 1.1 electron volt. The latest wide band gap semiconductors are those based on the new emerging material that have band gap typically in the region of 2 to 3 times that of the silicon. That's why it is we were moved towards the wide bandgap devices. So what are the benefits of wide bandgap semiconductors? Already I dictated. The silicon has been the dominant for many years, but is reaching its performance limits in a growing number of existing and emerging applications. Because WBG conductors can withstand higher electric field, they can sustain higher voltages. They can also operate at higher switching frequency. The latter not only supports improved performance, but also minimizes filtering requirements and allow the use of smaller external components. That means the faster switching energy is delivered in smaller packets, and therefore less energy needs to be stored in the circuit, passive and inductive devices. When compared to the legacy silicon, these factors translate into the number of benefits, including a smaller, faster, more efficient and more reliable operation. High voltage capabilities open up opportunities in higher power designs, while dramatically improved efficiencies enable the same performance in smaller form factors or allow improved performance in the same form factor. Efficiency also has an important on weight and ultimately the carbon emissions associated with the operations of the target applications. Many devices based on the WBG technologies also offer the benefit that they can operate at a higher maximum temperatures than their legacy silicon counterparts. So here you can see that what are the WBG materials are used for the semiconductor. A number of materials including the boron nitrate, silicon oxide and even diamond are all defined as a WBG materials. So here the GaN and the SiC are the two most prevalent WBG technologies in use today for the power electronic applications. However, the most prevalent WBG semiconductor devices today are those based on the gallium nitrate and silicon carbide. The band gap of these materials are around 3 times greater than that of the silicon at 3.2 electron volt and 3.4 electron volt respectively. So now one can understand what are the difference between the GaN and the SiC. So compared to the silicon, that has a band gap of 1.12 electron volt. So GaN and SiC are the compound semiconductors with band gaps that are around 3 times higher. So at 3.39 electron volt and 3.26 electron volt respectively. This means that both can support higher voltages, higher frequencies, though there are a number of difference between the two technologies that impact how they work and where they are used. So one difference between the GaN and SiC is speed in terms of electron mobility, how quickly electrons can move through the semiconductor material. So at 2000 centimeters square by volt, the GaN devices, GaN electron mobility is 30% faster than that of the silicon, while silicon has an electron mobility of 650 centimeters square per volt. So these difference play a part in dictating the benefits that each technology offers a target application. So the higher electron mobility of the GaN, for example, makes it much more suitable for high performance, high frequency application, something that further supported thanks to a very, very small percentage of chips being actually consumed by the gate electrode. So this ensures very low capacitance, meanings it is easy to achieve high frequencies. So which is why GaN semiconductors are widely used in RF devices that switch into the gigahertz range. So silicon carbide on the other hand. So I told you one of the project we were used with the silicon carbide devices only. So with its higher thermal conductivity and lower frequency of operation, so is more suited for higher power uh, applications, including the higher end voltages required in electric electron modes. So, and I mean electric vehicles, data centers, and some solar powered design, rail traction, wind turbine, grid distribution, and industrial and medical imaging that do not always require high frequency switching, but uh, do need higher voltage operation and improved heat dissipation. So here, I can say that both GaN and SiC are superior material to legacy silicon. 650 volt rated GaN offers a faster switching, integration, and lower cost, and is optimized for applications up to 20 kilowatt. So the higher voltages and higher temperature properties of silicon carbide makes it optimal for device over 1000 volt and applications up to 20 megawatt. So here, what are the difference between the GaN and the SiC? You just see that with respect to the high voltage operation, like various parameters it is given, like high thermal, I mean higher switching frequency, high temperature capability. You can see that silicon is also there. Then silicon carbide is also there. GaN is also there. You can see that based on that, we can fix the applications. So coming to the physics based on the model approach. So the modeling of the power semiconductor devices is essential to estimate their impact on cost, efficiency, weight, volume, and reliability, which are important performance indices of power electronic system. So these indices are mutually coupled to each other. For instance, higher power densities imply higher switching frequencies, which can lead to reduction in efficiency. So prior to the fabrication of the new structures, they can accurately investigated by modeling. It is essentially several physical effects that are high priority for developing the power semiconductor devices model, since they dominate static and dynamic characteristics. So in particular, the models for new devices must be able to mimic the device behavior in both static and dynamic conditions. However, if new devices shares certain related characteristics with the prevalent device, then it can be modeled by adjusting this approach. So one can see that the compact model we want to design. So in this regard, let us consider the outline of the physics-based model approach is shown here. So in the first phase, the device characterization is there. Is performed by experiments and numerical simulations on the model on the device structure by analyzing the results. So by analyzing the results, the model equations are formulated by physics by assumptions of deleted regions, field effects, charge transports, etc. The equations are performed by using the measured data as a uh, basis, and a large signal topology is to build. So the model is then validated by implementing for the target simulator and comparing the measured data with the simulated part. So the model considering completely only if it is able to capture necessary effects. If not, the model should be improved and the process is repeated again. So here you can see that the experimentation divide the structure into the regions, then governing equations employed to describe the regions, build the larger signal topology, parameterized equations, the model validations. So again, if fx is captured, so the model it will be completed. If it is not, so further experiments and device simulations it has to be done. So the analytically the models, on the other hand, are relatively quick for data processing, but have issues with improvement in accuracy. So this, the approach is dedicated primarily for quick evaluating the switching losses and based on the data sheet information, such as the input capacitance, transconductance, switching delay time, rise time, fall time, many parameters we can consider. So this method has been successfully adopted for comparison of different modulation schemes and device technologies of semiconductor devices such as IGBT, SiC MOSFET, GaN, like that. However, in developing the analytic model for switching power losses that are valid for wide range of operating points based on the datasheet measurements is not feasible. Since these losses ideally depend on the parasitics associated with the circuit and the package layout. So let us consider the comparison. So here you can see that the comparison between the wide band gap materials properties with the silicon. So I told amongst wide band gap semiconductor materials, the SiC and GaN are the more appealing for high frequency power applications. Some SiC devices are likely Schottky diodes are now battling with their silicon partners. So the superior advantage of silicon carbide in contrast with the silicon diodes permits device to work higher current density and minimizes the size and cooling system. By virtue, the wide band gap property devices assembled with GaN or silicon carbide can sustain to a greater extent, the greater extent heat and radiation still preserve their electrical properties. So silicon SiC has a much wider band gap than silicon and can handle higher voltages, faster switching, and display better efficiency. On the other hand, gallium nitride is especially attractive for high pressures. High temperature, high voltage applications because of its high electric field breakdown capability, good thermal conductivity, and high electron mobility. These are the advantages we can claim. So with respect to the comparison, one can see that with respect to the silica, the thermal conductivity. So the thermal conductivity with respect to the various materials, the various band gap materials. So it is given, you can see that among us, the silicon carbide, GaN, diamond, each has its own advantages and has a few disadvantages also. With respect to the power electronic applications, we are preferring always this one. So particularly the electron mobility is a feature that describes how quickly electrons can move through a semiconductor material. So a significant difference can be noticed from this. So here which suggests GaN to be more suitable for high frequency applications. On the flip side, silicon carbide has a higher thermal conductivity than GaN, thus theoretically suggesting that SiC devices to operate at higher power densities than GaN. Intrinsic high temperature capabilities SiC power devices enable better thermal management and a reduction of the volume of heat sinks and cooling systems. The capability of faster switching with the lower switching losses directly implies a volume reduction of passive components and heat sinks and hence higher power density. When higher power is a key desirable device feature, silicon carbide semiconductor material have an advantages over GaN. So like this we can climb many advantages with respect to the materials. So coming to the difference between the silicon carbide and the gallium nitride, here you can see that with respect to the silicon property of the comparison. So how it will be the breakdown electric field with respect to the silicon and the silicon carbide and higher voltage capability with a thinner and lower resistance semiconductor line. So the silicon MOSFET is 1 by the 300 times lower drift layer resistance, reduction in conduction losses as compared to silicon MOSFET and silicon carbide MOSFET. So the reduction in the conduction loss, the thinner is also 1 by 10 times. So and the multiplication of at the 100 higher doping concentrations. So this is the difference between the conventional and this one. So coming to the classification of the power semiconductor devices. So from the structure point of view, the semiconductor devices can be classified as a diodes, transistors, thyristors. For the sake of comparison between the silicon carbide, gallium nitride devices already we discussed. So we confine the discussion to the diodes and the transistors. So the power devices, the silicon, it is available Schottky, epitaxial, double diffusion, transistor BJP, MOSFET, IGBT is available. And silicon carbide, Schottky, epitaxial, and gallium nitrate as Schottky, epitaxial is available. And the transistors BJT, MOSFET, IGBT, JFET, all are available. Whereas gallium nitrate,
Alana.
Sir, your voice is muted, sir.
sir, now
Yes, sir. Okay, sir.
I do not know who has muted. Yes. Sir, can you hear me now?
It's audible, sir.
Yes, sir.
Yes. Sir, please inform me if any connection or anything is troubled. So we can climb many advantages with respect to each and every devices. So I just want to discuss here the WBG semiconductor applications with respect to the power versus the voltage rating. So this is I have taken from one of the textbook and it is there in the website also. So here you can see that the power rating from few watts to 10 megawatts. So how the voltage rating? So the voltage rating is if it is more, where it will be. So the silicon, gallium nitrate, gallium nitrate for silicon carbide and a silicon carbide devices. So nowadays, how it is useful for applications like motor drives, electric vehicle, and renewable energy applications, industrial robotic, medical imaging, industrial UPS. Many applications we were preferred for the voltage rating is more. And The GAN devices also we were using, but you can see that the power level. So this is this will give you a more idea about how the power and voltage rating it will be. So now you can look at it. The WBG semiconductor applications with respect to the power switching frequencies. So the power switching frequencies, the few kilohertz, it is famous only for the silicon devices, and more than 100 kilohertz. So we were operating with respect to the silicon carbide devices and gallium nitride devices. As the switching frequency increases, the power handling capability of the semiconductor often decreases due to increased thermal and switching losses. So this reflects the typical trade-off between the switching speed and the power semiconductor handling power handling capabilities. So with respect to the market potential for the WBG semiconductor devices, with respect to the gallium nitride and SiC opportunity, you just see that. So how it will be. So, and here you can understand that the total potential with respect to the devices, how it will be. And the replacement of legacy silicon, companies are increasingly replacing traditional silicon in existing applications with the WBG semiconductor devices, harnessing new power. Gallium nitride and silicon carbide are being utilized in new and emerging devices where the silicon falls short. The current trend is growing adaptation in various industries such as power electronics, automotive and consumer electronics. Everywhere we are started to use with the WBG devices only. The future projection is navigates, the estimates the combined market for silicon, gallium nitride and silicon carbide power technologies so exceed 20 billion actually by 2026. So this we have taken from one of the websites. And coming to the depiction of three basic diode structures. Here you can see that the SiC-based Schottky diodes are reported to be exceptionally strong in opposition to the leakage current thermal runaway, since requisite thermal temperature leap for increasing the leakage current is well over compared to the silicon pin diode. The silicon carbide power diodes are classified primarily three cases. So one is with the silicon carbide Schottky diode. The second one is a junction barrier Schottky diode, JBS. The third one is silicon pin diode. So the Schottky barrier diodes are capable of blocking the thousands of volts thanks to the larger electric field breakdown value of the silicon material. And JBS diodes are hybrid devices that integrates the engaging engaging of high breakdown voltages of pin diodes and merger voltage of on state of Schottky diodes. JB diodes are display Schottky like on state switching characteristics and pin like off state simultaneously. Moreover, JBS diode displays an increased surge current capability due to the conduction of pin regions. The P, I, and N regions. So we can structure wise how it will be the difference between the each diodes which it is indicated here. And coming to the structure of the 6 JFET. So this is what the structure of the 6 JFET. So the first one is represents with I mean the MOSFET. So first one is a planar one. The another one is the trench one. So when you are referring the SiC power switch to be marketed was SiC JFET, as its structure is simple and easy implement, the gate terminal of the SiC JFET is not isolated from the device body, and there is no reliability problem of the gate oxide and as observed in SiC MOSFETs. So SiC JFET is have primarily vertical structure, and therefore to increment the blocking voltage with the wide of drift region of device needs to be expanded. So they have more behavior. I mean, they have normal behavior, and once the conduction channel is established, the current circulates in both the direction to achieve an adequate blocking voltage of like 1.2 kilowatt. Usually, the applied reverse bias gate source voltages ranges from 15 volt to 20 volt. So this and all we come across through the device, I mean the device specifications. So allowing the formation of a drain source potential barrier by depleting of the channel region. So the SiC JFET device blocks the applied high drain voltage by depleting the drift region. So this is the one of the structure, and we can say that with respect to this is the one of the GAN devices that I mean the this is also the another GAN device. The basic structure, it is a representation, and the vertical GAN power diodes is also available. The vertical GAN power devices like how it is representing here. The schematic representation of the vertical GAN power diodes. What the first one is a Schottky diode, and the second one is a PN junction diode, and the third one is a vertical MOSFET. So I mean the three devices, according to the applications and the specifications, we need to prefer which type of device it is suitable for our applications. So actually vertical GAN MOSFETs present a favorable operation by providing normally off solutions, thus surmounting an I mean important drawback of any GAN HEMT based construction. So we need to see that this is what the schematic representation of the SiC and GAN structures, how we are representing with respect to the like a SiC, the substrate, how it will be, the GAN substrate, how it will be. So those things it is represented. This is the representation of structure of electron gallium nitrate. So here you can see that the structure, how we have taken like aluminum gallium nitrate barrier and buffer layers, how it has taken. So this is what a lateral two-dimensional electron gas. So channel formed for aluminum gallium nitrate and gallium nitrate epitaxy structure provides a very high charge density and mobiles. So this and all it is based on the construction. It works like a MOSFET except with better switching performances. So these are some commercially available devices in the market. So the SiC MOSFET which is available. So based on the I mean applications, we need to prefer. So how sometimes we require the reverse conduction in MOSFETs also. So that how it will be. It is represented here. So it contains the parasitic body diode dV by dt failure, high reverse recovery charge. So not ideal for off bridge switching. So and so like that many properties we can see that with respect to the both enhancement mode and cascaded mode. This is what the E mode GAN transistor data sheet. So with respect to that, we will come to know all the parameters. So based on that, the suitability of our applications, we need to select. So this is what the SiC MOSFET data sheet. So one of the data sheet which we were used for the applications. So this this device we were used for the development of the charges, onboard EV charges. So in our laboratory, we were developed such devices. And this is what the data sheet, how it will be the structure. And this is what the, coming to the merits, challenges using the WBG devices. So along the silicon-based semiconductor, WBG semiconductors have the capability for compact, robust, efficient power conversion systems. WBG semiconductor materials in electrical power switching devices enables a transformative influence on wide range of energy conversion applications. So I said that without WBG power semiconductor devices are thinner and display lower on-state resistance, which implies that the conduction loss and an overall efficiency, it will be superior as compared to the conventional silicon devices. So the WBG device provides many advantages like handling higher voltages, power switching, the faster switching, better efficiency, higher operating temperature. The power devices with the semiconductor material, silicon carbide, have less effect on functionality and continue to work even with the temperature rise up to 600 degrees centigrade. Very recently, one of our collaborator from IIEST Shibur and NIT Sikkim, they were developed the WBG devices for heating applications. So particularly induction heating applications, they started to use. So just we can say that the WBG power devices are smaller, faster, more reliable, operate at higher frequencies, higher power levels, higher voltages. So like that, we can claim many advantages. So the technology advances, these adults are likely to diminish, leading to even more widespread adaptation of WBG devices in various industries. Since with these devices are developed very recently and the cost of the devices is very high. So that's why still the people are reluctant to use. But definitely the cost, it will be reduces over the year. So to reduce the noise levels generated by the power converters, most devices contain an EMI passive filter whose use remain challenge towards the enabling high power density. So particularly the IAC Bangalore, our collaborator, Professor Kaushik Basu, he has developed a software for estimating the losses for WBG devices. So one is interested, you can go through. And IIT Madras also, they were developed many solutions, particularly EMI and EMC solutions for the devices. So the one of the thing is like I told you, like EMI. So it is an electromagnetic interference. The equipment should not be interface with the other systems.
So, for example, the turning on AC or DC power supply should not interfere with the radio operator. So, EMC that represents the equipment should operate normally, even with interference from the noise. So, for example, the AC/DC power supply should operate normally in noisy environment with the heavy machinery. And sources of EMI in power electronics is switching transients, parasitic elements, conducted emissions, and radiated emissions. So in this regard, we need to design the conductive EMI filters and the radiated EMI filters. The conducted EMI in the essence, so originate from normal operation of the switching circuits like on to off and off to on, impact of discontinuous current in the input sides or output sides of the converter, importance of the input filters for smoothing and voltage perturbations, and differential mode and a common mode EMIs is also available. And the advantages of the SIC and GAN devices, just we can say that loss reduction, elevated power density, extended operational range, enhanced switching dynamics. So this and the cost availability. So higher cost, these are the challenges. So higher cost and limited availability of the materials, integration with the existing systems. So and R&D effort, continuous research is needed to optimize the performance and reduced cost. So environmental and social impact, this focuses on improving efficiency and reducing the energy consumption for a positive environmental impact. So I told you in our laboratory, we have developed 6 kilowatt, 200 amperes, 20 volt welding power source we have created. I told you the weight of that welding power source is a 48 kg. By employing the silicon devices, that power source, I mean the same rating of the power source, it is around 120 kg. This is for your kind information, whatever the research which we carried. And apart from that, whenever we are chosen with the devices, so you need to study the behavior about the IV characteristics. So describes the steady state behavior of the devices. They are crucial for understanding the device performance under fixed operating conditions. Sometimes we require the pulsed IV characteristics uses the curved tracer for crucial measurements. Unique properties of the WBG devices require the special considerations. So sometimes the fundamental pulsed power source is also designed based on the WBG devices. So there also we require to have the attention to choose, to study the static characterization captures the steady state behavior of the under specific conditions. These conditions include a gate voltage, a drain current, junction temperature, then pulse test prevent the undue heating and maintained controlled conditions. So maintaining a device in an on state leads to conduction loss. So this loss impacts junction temperature and alerts the test conditions. Extends on state periods are difficult to manage in static test. So double pulse test and all people are effectively performing to understand the behavior of the devices. So the focus is the middle of each pulse for accurate measurement. Transient at the pulse start are just a means to an end. So middle pulse neglects the dynamic effects from turn on and turn off transients, avoids hard switching, helps to reduce the resonance energy. Static technique, static testing techniques also apply to conventional silicon devices like MOSFET and IGBTs. The difference is in the sensitivity and measurement accuracy. Silicon devices have higher thermal capacitance, allowing longer pulses, whereas the WBG devices is a smaller die size, results in lower thermal capacities. So the junction temperature plays a crucial role in device performance. Pulsed testing minimizes the temperature effects on the junction. Precise control of the junction crucial for accurate IV characterization. So the WBG devices are more sensitive to temperature changes than silicon devices. So particularly when you are measuring considering the devices RDS on. So based on that only we will have the losses. So lower the on-state resistance indicates the better the device performance, critical for evaluating the efficiency and thermal management in devices. So the maximum current capability determines the device performance under load. Pulsed test helps determines the maximum currents without overheating the devices. Important for ensuring the device reliability and safety. Critical for applications requiring the higher loads. The voltage capability is another key parameter for the power devices. So pulsed IV testing ensures accurate voltage limits are determined, helps in preventing device breakdown and ensures the reliability, and important for applications requiring high voltage tolerance. So the different characteristics when we were teaching to our UG and PG students like output characteristics, transfer characteristics, gate current characteristics, and drain voltage characteristics. So in this regard, we were referring the textbook called GAN transistors for efficient power conversion by Alex Lido, Johan Stridom. That textbook will give you the fundamental informations about the WBG devices. So similarly, the output characteristics. So the SiC MOSFETs and the GAN have unique on-state resistance and require specific characterization methods. So like a transfer characteristics, current characteristics, drain source leakage characteristics, drain source leakage characteristics. So like a pulsed setting should balance accuracy and device protection to prevent the self-heating or damage we need to. So based on the characteristics, one can summarize the drain and gate leakage characteristics identify the maximum voltage capabilities. Output characteristics identify the recommended operating current range. On resistance characteristics estimates the conduction loss in a converter. On resistance curve helps choose gate voltage or current for gate drive design. Transfer characteristics is an important for gate drive design. Indicates the threshold voltage, Miller voltage, forward transconductance. So these things will help you for choosing the devices. The another requirement by using the device is a gate drive for dynamic characterization. Yeah, good gate drive efficiently and reliably controls the power device, both in transient and steady state conditions, in fact, fault conditions also. So in static state, it keeps the device in an on state with minimized conduction losses, maintains the device in off state to prevent the unintended state changes. So the dynamic transient represents with the device from on to off or vice versa with the fast speed and low switching losses ensures acceptable electromagnetic interference, low voltage spikes and minimal parasitic ringing. So the basic functional blocks of the gate drive units is, so the gate driver ICs are buffer ICs, signal isolator and isolated power supply. So here you see that, for example, here you can see that how we are developing the gate drive circuits with the help of buffer. The isolator power supply is a gate driver IC. So signal isolator also we are developing. So in general, with respect to the microcontroller, it will provide the digital output so that it will be converted to the analog. Then we can feed it. So this is the way. And already we have discussed the WBG devices provides the superior properties over the conventional silicon, leading to high voltage blocking, low on-state resistance, fast switching speed, and low thermal resistance. So the WBG devices present unique requirements like high galvanic isolation capability, high immunity to common mode transients and ringing, high operating temperature capability. So the ideal versus a gate drive design. So ideal gate drivers should be tailored to specific device. Generic designs save time and cost, but may not be optimal. Matching a gate drivers with the devices, especially new WBG devices, is crucial for performance and sensitivity. So the impact of the gate driver design is to understand device characteristics is vital for proper gate drive design. Gate drives must meet both static and dynamic requirements of the devices. So the on-state characteristics minimize the on-state resistance or voltage and conduction losses. Proper on-state voltages selection is influenced by device and output characteristics. For example, silicon MOSFET and silicon Si MOSFET and silicon carbide MOSFET exhibit the different response to gate voltage increases. So similarly, off-state characteristics, the GaN HEMT devices and the silicon MOSFET devices have specific reverse conduction behaviors influenced by off-state voltages. The gate drive rating is silicon carbide and gallium nitride devices are typically have lower negative gate voltage ratings compared to silicon devices. So the dynamic performance influence are gate drivers, device, operating conditions, optimal dynamic performance requires a consideration of the device parameters. And so the key device parameters for switching performances. So high electron mobility transistors, HEMT devices, so that are used for many applications, including the cell phones, radars, electric cars, like that. So here the key parameters that it is specifications it is indicated. So signal isolator, isolated power supply, gate driver ICs, gate resistor, decoupling. So for dynamic characterization, provides a galvanic isolation, transfer control, and fault signals. So for that galvanic isolation capability, we are preferring common mode transient immunity. We are preferring, minimize the coupling capacitance to handle between the dV by dt. Fast switching WBG devices are preferring signal transmission, frequency range, propagation delay, like that. With the converter requirements, we are preferring. And so this is what the gate resistor represents with the controls the switching speed. So balance between the switching speed, losses, crosstalk suppression, and switch stress, capability to set different turn on and turn off resistors, power rating consideration for continuous operation in power converter. So decoupling capacitors, parasitic management. So all these aspects we need to be considered for the gate driver design. So the parasitics involves the switching communication loop also. So this is what the equivalent circuit. The power loop parasitics is also there. So like a resonance between the power loop inductance and the drain source capacitance, So this will create the voltage spike and a turn on transient. So that and all we needed to be studied. And so here we can conclude that. So the higher power means we can go with SiC devices with the compact size, and high speed means we can go with like gallium nitrate devices. So this both it will improve the performance of high frequency and high power converters. So these are the some challenges how we were using for the power converters like DC-DC converters. So how we are operating. So like compared to the ultimate objective is to improve the efficiencies only. So the paralleling the GaN devices in 13.56 megahertz class pi square inverter for high power applications. So this ratio of nonlinear capacitance to extremely added affects the turn off losses. So I mean this is the one of the circuit developed which is available. This is the prototype resonant inverter. So the voltage rating is 150 to 240 volt. So the applications. Now we will discuss about the applications. So far, we have discussed about the information of the devices. So in the device level, there are three examples. So the use of silicon carbide Schottky barrier diode as an anti-parallel diode of the silicon IGBT. So it is because of the better recovery performance of SBD, Schottky barrier diode, with respect to that of the silicon diode. So device paralleling of the silicon IGBT and silicon MOSFET. So this way is the silicon IGBT's lower conduction losses characterization and the silicon carbide MOSFET. MOSFET offers a low switching loss characterization or combined with in high current application with a compromised cost. So this property only we were used, and GaN and a transistor can be used parallel to both the silicon IGBT and the silicon MOSFET. So this is the achievements with respect to the better conduction, switching performance like that. So these are the some devices were used for the isolated applications. So this is what the hybrid circuit configurations with respect to the based on the DC-DC converters. So based on the DC-DC converters. So the first one is the silicon and the silicon carbide based. The second one is the silicon carbide and the gallium nitrate based DC-DC converter. And we can see that this represents the WBG devices in EV operations. So because this is only the topic, it is good idea to study the applications of WBG devices in electric vehicles. So based on the power rating of different power electronic interfaces. So here we can see that the silicon carbide competes with the silicon in a higher range of power, but lower range of frequencies, while the GaN competes with the silicon in a lower range of power, but high frequency range of application. So actually this diagram explains about you the power frequency plane of silicon MOSFET, IGBT, silicon carbide and gallium nitrate for different power electronic interfaces in EVs like a traction inverter, boost converter, mild hybrid inverter, auxiliary system, onboard charger, like that. So, and therefore, one can understand that the power electronic interfaces in EV, then we can realize in a right place for SiC and GaN there. So this diagram represents with how the WBG devices were used. The traction inverter, the power DC-DC converter, the battery charging, onboard charging, AC charging. So, and how it will be the motor control traction inverter, and how it will be the high voltage DC-DC converter, and how it will be the onboard charger topologies. Those things here it is represented, and this represents a SiC-based inverter, the commercially available SiC-based inverter. So actually, this is what the model developed by the Tesla SiC power module in by Tesla. So here SiC-based traction inverter and power management DC-DC converter in Camry by Toyota as a road test prototype in 2015. So actually, and the WBG inverter buggy vehicle by Nagayo University and Toyota as a road test prototype. So, this table will provide the comparison of the EV subsystems between the silicon-based and WBG-based devices. So the motor drive and onboard converter charges with respect to the power density, like the silicon and the WBG, the efficiency, switching frequency, we can compare. So coming to the motor drive applications. So the WBG devices, which is used for the motor drive applications also. The integration of electric motor with motor drive improves the power density and reduces the system cost. So wide bandgap devices operate at higher temperature and offer higher efficiency. And particularly for the induction motor, nowadays, even for the megawatt applications also, people have started to use the induction motors. So are widely used in aerospace, robotics, automobiles, and off-road vehicles like that. So in this regard, we can understand electro-hydro actuators also. We were started to use the devices. Particularly like radially house mounted and axially house mounted, radially stator ion mounted. So all these applications we were started to use with the WBG devices for effective operations. So comparatively higher cost than silicon devices, and but savings in other areas like cooling, passive components. So low switching losses, higher power density, and high temperature operation. So the induction motors are modular, providing better integration on curved surfaces and fault tolerant operations. Different inverter topologies is available. We started to use that. And one of the topologies, like a 6-leg inverter with a single DC link, and a 4-leg inverter also people are started to use. And this is represents the standard fault tolerant 3-phase inverter topologies for induction motor drives. And this table will provides you the silicon carbide switching device option for induction motor drives with respect to the various factors like voltage, current, temperature, structure, fabrication, thermal management, availability, like that. So, and different manufacturer is also there. So these are the different manufacturer. Based on that, we need to choose how we can have the devices with respect to the GAN. The challenges and opportunities are issues include synchronization of multiple controllers and the need for sophisticated cooling systems. So in general, for EV applications and all, we were used with permanent magnet machines only. So this provides the higher efficiency, and in gist, the WBG devices which provides with low inductance, high speed, high ambient temperature. So how it will be the requirements and applications, it is indicated here. So with respect to high pole count, high speed motors with a high torque density, so megawatt levels, in fact, we can use it. This is the representation of the motor drive applications: motor, power cable, inverter, and a rectifier unit. So, and technology with respect to the renewable energy technology, also people are started to use with the WBG devices. The challenges is switching speed of the WBG devices will incur increased in electromagnetic interference. So renewable energy sources, if WBG based power converters are not properly designed. So already all these points we were discussed. In fact, the solar PV applications, wind turbine applications.
Not audible.
Sir, it is not audible, sir.
Sir, it is not audible, sir.
Sir, your voice is not audible.
Yes, Tony sir, audible. Yes,
Participant,
Tony sir,
kindly
audible.
Okay. Kindly hold on. We will inquire with the chief guest.
Okay, okay. Sir.
Can you audible now? I do not know how it is going with the mute operation.
You are audible right now.
Sharing the content. Can you able to see, sir?
Yes, sir. I able to see.
So this is the GE 1 megawatt solar inverter installed in Berlin. And this is the representation with respect to the GaN devices in the battery energy storage systems for the residential applications, how they are using with the grid connected inverter and followed by the DC-DC converter. So in fact, we had many experimentations with respect to this circuit. So the bidirectional power transfer and all we were verified with respect to this circuit. So the second circuit is the propelled topology in a single phase configuration. And this is what the series stacked structure in a three-phase configuration. So this is the represents with the three-phase grid and multi-level power converter. That means a three-level NPC converter and followed by the buck boost power converter. I mean the three-level buck boost power converter. So when it is operated in buck mode, I mean here the voltage is less, here the voltage is more, then it is operated as a buck. So I mean the current, it will be going this direction. Boost mode means this direction. So this is the standard topology. In fact, we were using for the battery charging applications. So thank you everyone. So I just want to summarize. Actually, I have provided the detailed review on the potential of wide band gap semiconductor devices in power electronics. The WBG materials such as GaN, SiC have seen an upsurge and are projected to be widely adapted in the semiconductor device market. So these materials find their use across many industries depending on their device power rating. In semiconductor devices rated from 15 volt to 650 volt, silicon remains a strong candidate while being
also reliable and economical. Silicon carbide is more suitable for high power applications. Example is a DC-DC converters in electric vehicle operations, and GaN for low power applications like mobile device chargers. So they are being studied as an alternative to solution. I mean, the alternative to silicon primarily due to the interesting electrical properties such as 3 times higher band gap and around 10 fold higher critical electric field compared to that of silicon. So WBG devices are smaller in size by virtue of 10 times the thinner drift layers compared to silicon devices of specific voltage capability. Moreover, the higher switching frequency of the SiC and GaN devices allows the reducing the size of passive components that leads to an overall decrease in the size of the system. So the reduction in size would imply requiring fewer materials that will make WBG devices more sustainable. So the cost of WBG materials remains a challenge as the device are 2 to 3 times more expensive than conventional silicon-based devices. Therefore, to make them cost competitive against silicon counterparts, the demand and manufacturing of WBG devices needs to start to gather pace. So indeed, the WBG semiconductor devices market size, which will be valued more in the future years. So in the near future, WBG devices will continue to make progress into the predominant position of the silicon-based devices and unleash innovative solutions for power electronic system that are attainable with the silicon technology. So participants, thank you for your patience and listening. So any doubts or any clarification, please interact with me. I have given just an overview of the wide band gap semiconductor devices in power electronic applications.
Thank you so much, sir. Participant, if you have any queries, you may post the same in chat box. Participants, if you have any queries, you may post the same in the chat box.
Sir, good evening, sir.
Yes, sir.
Sir, this is Dr. V. Kamachkaran, Professor Electrical Department from Knowledge Institute, sir.
Yes, sir. Please, sir.
Sir, I have a small doubt in your topic, sir. Actually, we are having some composite materials like metamaterial in specifically for applications like solar, there is solar cell or photo detector or any communication devices. We are nowadays we are preferring metamaterial composite materials. Whether this comes under WBG, sir?
Definitely, sir. Actually, you must see that how it is suitable. So initially, I have discussed some properties of the materials. So with respect to that properties, like for example, the silicon, I mean the thermal conductivity, band gap, breakdown field, dielectric constant, electron mobility, drift velocity, intrinsic carrier concentration. So those parameters, how it is placed with respect to your material, that you can see that nowadays many nanomaterial people are started to use to bring, to bring the competitive for the conventional silicon devices. Only thing is, here we need to see that how it is suitable for the power electronic application. I have
I have referred one article from Energies. So I think from Government College of Technology, Coimbatore, maybe the author name is Michael Lastio. So he has given the overview. From the overview, he has given very nicely about the properties of the wide bandgap devices with respect to the power application.
Sir, whether we can have any software, any kind of software is there, any open source software is there to analyze these type of that is these type of materials. Why? Because we are belong to electrical department. Whether we can do any kind of analysis in terms of these materials, there is based on these power devices. You have given some overview about the improvements in the efficiency of the converter, sir. Whether we have any kind of software to analyze these materials.
Sir, actually, the software which you are asking about for the simulation, correct?
Yes, sir. Yes, sir. Whether it is possible, sir.
If you are modeling the devices, mathematical modeling, if you are done based on the equivalent circuit of the devices, by incorporating all the parameters of the devices, then simulation software, any software you can use it. But nowadays, I hope the solution, direct solution is given by Altair and Spice Solutions that they are given.
Okay, sir. Thank you, sir.
Mute your mic. Kindly mute your mic.
Thank you, sir.
Thank you very much, sir. Thank you very much, sir. I think we have done with the queries and things. Thank you so much, sir, for accepting our invitation for this ATAL FTP and providing your valuable speech for this FTP, sir. Thank you so much for your love and guidance, sir. Thank you, Senthilkumar, sir. Senthil, sir?
Sir, can you hear me?
Yes, sir. Now we can hear you, sir.
Yes. Thank you, everyone. The most of the information I have taken from the textbook and internet and a few articles. So here I just want to give the overview of the information. Maybe at the I will share some review articles to the coordinator. He will share the same to you. You can refer those articles. You will get an idea of using WBG devices in power electronic applications. Thank you, everyone.
Thank you so much, sir.
Thank you.
Please share PPT.
Yes.
Dear participants, all the presentations will be shared to you at the last. You need not worry about things. Whatever Sir is also going to share, we'll also share the same to you. So you need not worry about the details. The thing that should be shared now. As of now, we have posted the feedback link in the chat box. Session 1 is officially over now. The same link, the session 2 will be starting by 8:05 or 8:10. Go ahead so that you please look over the chat box for the feedback section. The feedback link is available. All the feedbacks will be shared only in the feedback link. So please make a note of it. I request all the participants to fill the feedback form. It will be available only in the feedback link. It will nowhere be shared in the WhatsApp link or somewhere. Thank you, participants. Participants, within another 5 minutes, we will be seeing through the lecture of Dr. Umashankar sir. So you may fill the feedback form as of now. Kindly take the time and fill the feedback form. Another 5 minutes, we'll be starting with the session 2. Thank you.
Hello, sir.
Okay, Tony sir. Okay.
Sir. So where you have posted the feedback?
The chat box is posted. The feedback is posted in the chat box, sir.
Okay, sir. Thank you.
Kindly check the chat box for the feedback process. It will be available in the chat box, so you may fill the same.
Sir, I am not finding chat box or feedback link. Feedback link is not showing.
Rajendra Singh sir, you may check in the chat box, sir. It is available now. Please check over there.
Where, sir? I am not getting.
Are you connected in mobile or in PC, sir?
Laptop, sir.
No, sir, it is still not available. It is not still available in the chat box, sir.
Sir, we have posted. I think other participants have got through the feedback link. Is that so? Participants, have you all got the things in the chat box? Yes, sir.
Sir,
No, sir.
I have
We
just
have not.
shared the screen too. I have just shared the screen too. You can see that it is there in the screen too. You can just view that. I hope towards the right, Hubert Tony Raj. Below that, it has been mentioned https://forms.office.com/r/DD4DS48EAD. I hope you are viewing that.
Yes, sir. Dear participant, within another minute, we'll be starting with the session 2.
Sir, I have a problem. I am not getting the chat box here.
Sir, I will rectify it out. You may please text me in the WhatsApp, sir. I have noted your name so that I can mark your attendance even. Okay, I can mark your attendance even officially, no problem. You can text me in the on the WhatsApp link you saw. I will also notify it, sir. No problem, sir. No problem.
Okay.
Sir, Umashankar, sir. Am I audible, sir?
Yeah, you are audible.
Okay, sir. Sir, are you able to share your screen thing, sir?
Hello?
Can you please check it out?
Yeah, I can share now.
Okay, sir, please, sir.
So is it visible?
Yes, sir, it is visible, sir. Can I officially
Visible, sir.
start? Can I officially start with the welcome address, sir?
Can you check now?
Yes, sir, it is visible, sir. No problem. Can I officially start it, sir?
Yeah, you can start it. Yeah.
Thank you very much, sir. Dr. It's time to welcome our chief guest. Our chief guest is Dr. Umashankar Subramaniam. Dr. Umashankar Subramaniam is a professor and distinguished researcher in Renewable Energy Labs, College of Engineering, Prince Sultan University, Riyadh, Saudi Arabia. He is a co-founder and assistant director of the Renewable Energy Lab, which is directed towards renewable energy and EV related research and projects as per 2030 vision of Saudi Arabia and United Nations SDGs. He is also a part of 2030 International Steering Committee for Global Ranking and Global Distinguished Experts at the Global Education Policy Network towards Sustainable Development. He is a chair, a co-chair of international workshops and prestigious international conferences. Previously, he worked as associate professor and head of the Department of Energy, VIT Vellore, and he has 20 plus years of leadership, teaching, research, and industrial R&D experience. Also, he has worked as a senior R&D engineer and the senior application engineer in power electronics, renewable energy, and electric drives in top companies like General Electricals, Factron. He has also taken leadership roles like head of the department, international ranking and accreditation, COE establishment, quality assurance and times, higher education SDGs, industry engagements, placement and internships, assistant director, director of research, industry collaborative projects, chair and vice chairman of IEEE professional societies. He is a senior member of IEEE and a member of Power Electronic Societies and ISTE. He is an ex-com member of IEEE PES Saudi Arabia section from 2021 and an organizing member of IEEE PELSIS 2021. He is a vice chair IEEE Meta section and chair IEEE student activities from the year 2018 to 2020. He was an executive member and vice chair of IEEE Mass Young Professional from 2017 by the IEEE Madras section. He has published over 250 research papers in national and international journals and conferences. He has also co-authored and contributed 12 book chapters and 12 technical articles on power electronics applications in renewable energy and allied areas, and holds 20 research grants, 5 consultancy projects, 2 US patents, 2 IPs, and 1 Indian patents. He has held positions like editor in IEEE Access, Helion Cell Press, Springer Nature, Alexander Engineering Journal, IETS Wiley, and other high-impact journals. He received Danfoss Innovator Award mentor during the year 2014 to 15 and 2017 to 18. Research Award from VIT University during 2013 to 18. He has also received an INAE Summer Research Fellowship in the year 2014. Under his guidance, 24 PG students and 25 UG students completed their project work. He also guided 12 PhD scholars in collaboration with industries. He There has been collaborative government grants and industry research products like sustainable PSUs, campus, and sustainable microgrid and eco-change electric vehicle development in Saudi Arabia and in India. AI-based prediction and condition monitoring, AI-based fault diagnosis, power quality audit in Southern Railway, EMI EMC in solar PV inverter, power quality analysis of industries with InPhase Bangalore, Enrich India Chennai, wind solar hybrid systems sponsored by MNRE with CVET, Qatar, VAT Danforth Joint Energy Management Project, Smart Energy Metering, and e-mobility and charging infrastructure for EVs funded by government and industry. He is a proud alumni of PCC from the year 1997 to 2001, the batch of EEE, and an outstanding alumni of VAT. Did his MTech during the year 2002 to 2004, and he did his PhD in the year of 2010 to 2013 in the same VIT University. Thank you, sir, for being with us. Now, the session is all yours. Thank you, sir.
Maybe can you mute? Yeah.
Participant, I think someone has been turning on their mics. Please kindly mute yourself. Sir, you can go ahead, sir. Please, sir. Thank you, sir.
Okay. Am I audible? Right?
Yes, sir. You're audible, sir. You're clear, sir.
Thank you so much for this faculty development program. And so I would like to share some of the things happening in the industry, as well as especially for the EV charging industry, and what's really going on and how the power electronics is playing an important role in this. Because nowadays, if you see, we are talking like power electronics is saturated or outdated. But really, if you see that the power electronics is getting a momentum now, because everywhere they are talking about the electric vehicle and fast charging technologies. Even if you look at it, even in like all the highways in India, you might have seen like different charging stations, especially 50 kilowatt or 25 kilowatt, like ultra high fast or fast charging stations. So mostly they require these kind of power electronic technologies. Even though the technology is from the Europe or Western side, mostly if you see that what we are doing is we are acquiring the technology, or we are importing the technology from the Europe or China, and we are incorporating in India. We do not have a customized technology development in India. But this is going to be the future, because it is estimated that there is going to be a drastic increase in the EV, especially the two-wheeler, then three-wheeler, as well as in the four-wheeler sectors. So I think this session will give you just an idea about what's really happening in this field and what kind of technology they are using in this. So I want to just introduce myself. Like, I am from Renewable Energy Lab, Prince Sultan University. So I'm here for the last 7 years here. Previously, I was at the VAT University as a head of the department. And I have some interest in the renewable energy, basically. But now, if you look at it, the technology is completely changing. And so I have also diversified interest in EV, as well as little more interest in the artificial intelligence domain as well. So the motivation, I hope you might be knowing, like why we going for the EV is to combat the climate related issues. But you might be knowing what's really happening around the world, right? Like for the past 5 years or 10 years, what's really happening. And another thing is the policies also keep on changing, because you might be knowing what's really happened in the US last 5 years and what's really happening now. So the policy is changing. So it depends on who is going to provide the policy, or who is going to impose the policy. So developing nation is the one which is the motivation for the electric vehicle, mostly the Western side. But now it is reversed because of the new president elected in the US. then lower cost in the conventional vehicles, then air pollution. So this is the talk of the town or talk of the world, almost since from the COVID time. So they were talking like this. But is there any useful implementation is happening? So that is a big question mark now. Even though we have introduced like a 25% of the EV in India, but still we are facing the same pollution level. Major country, if you see that they were focusing on how to reduce the or how to come out of the oil, that means independently, and how to focus on carbon neutral things. So even the carbon neutral things also nowadays you can just get it as a certificate without incorporating it. So this is what really happening. Everything is in the paper, not in the implementation. Then another huge challenge for this motivation is lack of infrastructure. So especially the grids. So this is also another issue. So what we are facing exactly. I hope so. You also might be experiencing or you might be come across all these factors. Okay. So why we want to transition to electric vehicle since from the 2018, just before the COVID, and what's going to happen by 2030? It is the predicted one, but we are exactly in 2025. Do we achieve this 2025? No, we didn't achieve this. Why? Because if you see, as per this projection, we should have achieved, I think, 75% of the battery electric vehicle, but we are in 2025 now in the beginning, but it's not so. I think we achieved only 25% in the battery electric vehicle or plug-in hybrid vehicle, but not we didn't completely remove the IC engine. So it's not so. It's because of the global scenario, what's really happening. So we cannot say that really it's going to be because of the projection what we are doing it. So sometimes projections also fail, or whatever you predict also sometimes it fails. So I think you can see from the data itself. So what they projected and what we have now, it is failed. There are a lot of reasons are there. So it's international level geopolitics, and not only that, there is like a lobby for the battery and other related things, because who is going to manufacture the battery? And if you look at it, so mostly it's dominated by the Chinese and European vendors. So that's another challenge. In terms of India, if you look at it, so there are only few companies like Exide and other companies, they are into the manufacturing of the battery, and we do not have any mega factories, okay, like Tesla and other companies, BYD in China. So hopefully, I think India is supposed to have like a mega factories, then only we can achieve in this area. So I just want to show you one of the videos of why we are going for this EV.
Kindly mute yourself so that we may hear whatever there is a speaker is speaking. Kindly mute yourself.
Okay, so I just wanted to explain. Okay, that's fine. If you look at this, so Ashok Leyland, if you see that they have introduced, they have a tie-up with the Sun Mobility. I hope you might be knowing, some of you. This is something like how you can swap the batteries. So how far or how long it takes to swap the batteries. Because you know very well, so it's maybe for after some time you need to swap or you need to recharge or something like that. So this smart battery from the Sun Mobility, if you see that it has a lot of features, and quickly you can replace it. So this is what related to the Sun Mobility. It happens just in 3 minutes. You can swap it. This is the tie-up between the Ashok Leyland and the Sun Mobility, and this is one of the breakthrough in this domain, especially in India. Okay, which is happening. And if you look at it, this Ashok Leyland as well, they have a tie-up with IIT Madras. So they have some project is also going on in the IIT Madras campus. Next, this is about the battery. So now we focus on the charging. So why the charging is important? Because once you have deployed all the electric vehicles, so you need enough or abundant charging stations. So as of now, if you might be knowing, you have a lot of petrol stations out there. So that many charging stations we supposed to have in the future. So how it happens? So that's what the question now. Even though I think Ministry of the central government, they have imposing a lot of incentives and a lot of policy making things are happening. But still, if you look at the growth and because it requires a lot of investment, huge investment. So only the big players are doing it, whereas the small players, I think it's very difficult for them to engage. Out of this charging techniques, so you can have like a 3 different kind of charging. So it depends on the location. So for example, slow charging. So whenever you come back from your office or your employer, so then you can just connect your car or two-wheeler to the charging in your home itself. Okay. So it doesn't require fast charging because you can just connect it and you can charge throughout the night also sometimes. Whereas in the medium charging and fast charging is required. Medium is required during the office hours, like when you go to your office and you are parking your car in your office. So that time you may need a medium charging because you will be in the office time. Maybe you might be want to go out in the afternoon also. So that means you need a medium charging applications. Where you need a fast charging is whenever you are commuting from the one place to another place, you need a fast charging because you may not have a sufficient time to wait. Okay, so for the charging, so you cannot wait overnight or you cannot wait 7 hours, 8 hours. So you need a very quick or fast charging. That's why you might be seeing in the highways nowadays. So you can, whenever you come across, you can see that it is around 50 kilowatt chargings. Okay. So in terms of charging, if you look at it, so I'm sorry, there is A is automatically talking. So this is the kind of negativities for the AI also. AI is automatically talking. Okay. So as far as the EV charging is concerned, I hope all of you are listening, right? So I believe that you will be listening. So there is a e-mobility. So charging is done by the ABB. ABB is the pioneer in this particular domain. Why? Because so they have introduced the kind of charging solutions in the early like 2000 or something like that. Then if you look at it, they also have a tie-up with so many countries as well. So basically they were from the Sweden and like Europe domain. And now if you look at it, so they have incorporated their charging solutions as well as in Chennai also. That means in India. So they have a different kind of thing. So you can just have a look at it. So starting from bus, then commercial, industrial, then apartment, residential charging or fast charging in the roadside. Okay. So that means whenever you cross your toll, right, you can charge it also. In the toll also you can charge. So like that, they have different kind of facilities also available. Out of this, if you look at it, so there is a different kilowatt ranges is there. So kilowatt represents how fast you can charge your vehicle. So starting from 24 kilowatt to 600 kilowatt is also available. So you can just see one example also how you are going to charge very quickly from the ABB technology. And then another side, if you look at it, so other than the Western and Euro, so there is a equal competitor is there. For example, China. China also they have like with tie up with the State Grid Corporation of China. So if you look at it, they have developed a 900 kilowatt charging, which is so far it is a very fast charging and with a higher power rating. Apart from that, you can also see GPT, then Chadamo or Tesla. So many players are also there. So the fast EV charging is done by the ABB technology. If you look at it, so not only That means the bus, they have the battery swapping technology, but also you can have a fast or flash charging technology that you can do it in 20 seconds itself. So let us see one of the videos of how you are doing this fast charging very quickly. Are you able to listen the audio? Are you able to listen the audio?
No, sir. Audio is not. We are not able to listen to the audio, sir.
Now?
No, sir. No.
Now it's coming?
No, sir. Yeah, your voice is audible, sir. But video which you are playing, sir, that audio is not.
Okay. This is a kind of technology you can see, whereas we have seen the battery swapping technology, right? So that is a one technology. The other technology, if you look at it, so this is so-called high-speed charging technology. You can see how it is, the bus is coming to the stop and how it is charging. So this is done, the demonstration shown in, I think, in the Europe. So you can see like technically what's really happening for the 600 kilowatt within 20 seconds. So this is so-called smart mobility and smart charging technology. And you can see that how the passengers are coming in and they're going out, and how the charging is taking place in between the time. Okay. You also have all these technologies which is deployed in the bus itself in the top rooftop. And if you look at it, each bus station, it has its own charging station also. So now if you see how the moving arm is connecting, and within 20 seconds it is charged. So that means by that time the passengers are coming out and coming in. So within that time period, you can see that it is how it is charging. So this, if you see that this is not happen without this AC to DC converter or energy storage or any other power supply unit. Okay, without the power electronics, it's not at all possible. And you also have some traction devices which should be deployed in the bus itself. So, okay, in order to control the traction motors. So this is just example of a high speed or a flash charging technology. Even this technology, if you look at it, this is been established in IIT Madras. I think one of the research project by the IIT Madras as well as ABB. The another one is about the wireless power transfer technology. Hope you might be knowing many of you if you are using your smartphone, especially the Samsung and iPhone. So you can nowadays you can charge using the wireless, right? So this is the same thing when you apply to the electric vehicle as well. So how you can charge it. So here also the like different kinds are there, like inductive and capacitive, but mostly if you see it's based on the high voltage and the high frequency range. And the one advantage is you do not require any cables. Okay, maybe it's like looks like aesthetic. Okay, so I think in a real estate point of view, I can say it is aesthetic design. Here also, if you look at it, so you can have like a different kind of charging. For example, static charging or opportunity charging or dynamic charging. In fact, the first two, if you look at it, this has already been established, whereas the last one is it is under the like trials. Okay, many countries they are doing this trial. The one you are seeing in the left side is nothing but your parking infrastructure, so where you can charge your car. Whereas the second one, if you see on the road, they have deployed this particular WPT infrastructure. So throughout the road, so that while the car is moving, you can charge it. So this is what the advantage of going this. But they are doing a trial now, and it's not a. The next thing is about India already has established the first public EV charging. So I hope you might be knowing. This is especially if you look at it, it is during the COVID time they have established. So this is also another thing. So I think nowadays they are allotting the parking lot also for the EV charging. So far what we discuss is in terms of general, like what's really happening in the field and what are the different EV charging and what are the different kinds of charging, like You can charge it in your home, or you can charge it in your office, or you can charge it while you're traveling from one place to another place. So now what we are focusing is, maybe many of you might have come across if you are in any part of the India. I think Xeon is doing so many charging stations whenever you travel in your national highways. Okay. And this is some example related to the wireless. So I just want to skip. I want to go to the topic now. Okay. So the main thing is about WBG, wide bandgap semiconductors in the EV system, especially when you talk about the what is it, OBC, onboard charging. So how it is going to transform the world? Okay, so whatever you have seen is in the generic, and now how the power electronics is going to transform the world. So that's one you are going to see now. I hope most of you might be knowing about the power electronics or semiconductor devices. So whenever you talk about the power electronics, always we used to start from the diode, thyristor, and then next we go ahead with the IGBT, that means the BJT, then IGBT, then MOSFET, GTO, etc., IGCT, then like that we talk about it. But now if you look at it, so even they want to change the material itself, okay, the semiconductor material itself. So how? Usually, if you see that we dealing with the silicon, right? So, or mostly it's germanium in the olden days, silicon or germanium, right? But if you look at it, so now what we need is our life is also very fast nowadays. Everything, whatever we are doing is like fast now. The same thing is applicable for this power electronic devices also. So the devices also we want very fast. So why we want very fast? There are a lot of constraints are there. Why? Because so far we operate the power electronic devices with the low frequencies or medium frequencies. So, but we want to operate these devices with a very high frequency. Why? Because there are a lot of factors involved while you design the power electronic semiconductors. So what are the important factors you might be knowing, right? So this is nothing but passive devices like capacitors and inductors. If I am operating at very high frequency, so I can just avoid using the bulk size. And not only that, I can eliminate the losses also, okay? Low switching frequency, if you're using it, sometimes if you see that there is a misfiring or losses also happen. So that's the reason. So we are switching to the high switching frequency related devices. Excuse me. Not only that, but if you look at it so far, what is the voltage level they are using for the charging? You might be knowing like a different kind of batteries they are using in the electric vehicle. So what are the different kind of batteries? So far we started with the 12 volt. Then we gone with the multiples of 12, like multiples of 12, like a 24. So multiples of 12, like 24, then 48, like that it goes on. So now if you look at it, so what is the voltage level we are using? Anybody knows? Is the
48.
answer?
48 volts, sir.
48 volt. Okay, but I'm not sure now what is the voltage level they are using. Okay, 48 volt they are using in some of the vehicles. Okay, so anybody else know like a Mahindra vehicles, or when you jump from India to US, like a Tesla, what they're using when you're jumping from India to China? BYD is there. So
60
what is the voltage they're using? Anybody know? Because that is the ultimate reason why we are going for this WBG. Okay. So wide bandgap semiconductor is required only because of the voltage level we are switching now. Okay. So that's the main reason why we are going for this WBG. Otherwise, we can use with the existing itself. Okay. So I will just explain while going through the slide. Okay. So why WBG? WBG means wide band gap. So what is mean by wide band gap? It's nothing but, So there is a band gap is there. You might be knowing, right? Mostly you might have studied in the electronics or power electronics. So the more the band gap, if you look at it, so the more the voltage in the offstate. So it can withstand very high voltage. Especially if you take SiC or GaN, okay, the silicon carbide or gallium nitride. So they have a band gap is very high. But if you look at only the silicon, it is about 1.1 electron volt. But if you look at these WBG materials, it's more than 3 EVs. So that's the key advantage when going with this. So higher breakdown voltage. And I hope you might have studied about the forward characteristics and reverse characteristics and why you need high breakdown voltage. I think you can easily understand. The next thing is about the switching speed. Our world is also fast and we are also fast. So that's why we also need the switches also fast, especially the power semiconductor devices. So when you compare the SI, so I think we want to achieve the 3 times the switching speed. So that's the reason why we are going for this SiC and GA. Then another thing is about the thermal conductivity. So SiC, if you look at it, so it's more than the silicon alone. That means this is also almost 3 times. Okay. So these are all the very important factors when you are designing the current electric vehicle OBCs like onboard chargers. And you can see in the right side, so you can see the x-axis is the switching frequency and y-axis is the power output. And you can see the clear distinction between the silicon and SiC and GA. So how it is distinguished. So what kind of application they are using, starting from your commercial air conditioning, or you can look at the washing machine and conveyor belt or truck. Okay, and starting from your power system, power supply systems, electric train, renewable energies like wind and solar, then vehicles. Okay, then talk about the storage, then
Sir, Umashankar sir. Sir, Umashankar sir.
can you hear me? Hello?
Yes, sir, we can hear you, sir. Sir, your screen
I
is
don't know
not
what.
visible right now.
No. I don't know why it is disconnected. I don't know, really.
Okay, sir, no problem, sir. You please share once again, sir, please. No visible, sir. You can share, sir.
Is it okay?
Yes, sir. It's okay, sir. You can go ahead, sir.
Okay. So you can just watch this graphical interface like silicon and SiC and GaN. So how they split it into, and where the OBC, that means onboard charging, or EV charging, that means the offboard charging is coming into picture. So whereas if you carefully look at it, so wherever these three are intersecting, so we need the OBC in that region. So that means combination of all these things. Okay. So that is the prime region. So where you are operating your switching frequency is between 100K to 1 mega. And if you look at the power output, it is around 10K to 100K. So that means a 10 kilowatt to 100 kilowatt. That is the range you need for the charging applications. You do not need a high power output also. You need this range only. And especially you need to operate between the 100K and 1 mega. So this is the another important thing. Okay. Then, so why WBG is over the silicon? So there are a lot of points we already pointed out, like switching loss, then vehicle range. If you look at it, so how the Tesla is and how the Mahindra is and how the other companies are playing or doing it. Okay. So what is the range is required? So suppose if you buy one thing from the Chinese, so you might be knowing what is the range of kilometer you can operate it. At the same time, if you take the Mahindra or if you take Tata, or if you take Tesla, so how the range or how the BYD is having a range. So the range is very important for any electric vehicle. Okay, so that's the thing which is very important here. And not only that, so I already pointed out regarding the band gap and mobility, then thermal conductivity, then velocity, then breakdown voltage. So if you look at it, so silicon is like coming in the small range. You can see the blue, and SiC is coming in the red region. And if you look at the GaN, gallium nitride, so it is coming in the, it covers the most of the region. So it has a wide range. Okay, this is an important comparison of your GaN, SiC, and Si. And the same thing you can look at in the table also. Excuse me. So you can see different parameters also, like breakdown, short circuit, then thermal conductivity, threshold, then die area. What is the die area is required? Reverse recovery charge, then reverse diode effect. So many parameters are playing a very important role, even though the voltage of the GaN is very less, like a breakdown voltage. But if you look at other properties like avalanche and short circuit, it is it doesn't have, right? So that's another key point you may be consider comparing the SI and SiC. The next thing is about you might be knowing about how the onboard charges will be. So usually what you do is you go and park in your office or in your home and you directly connect the charging plug, right? So when you connect it, what's really happening? Because you are going to connect your plug point that is from the AC. And once you connect that AC plug point, so what's really happening inside? So that you're supposed to be knowing, right? There is a different stages of energy conversion is there, and you also have like different power electronic converter circuits will be inside. So how your AC is converted to DC, then DC is again controlled or as converted as a controlled DC to shoot for your battery charging. And again, from the battery, how the same DC has been converted to AC to drive the drivetrain as well as the motor. Okay, so this is a very important thing. And if you look at it really, there are different kind of things. For example, so far I asked one question, right? What is the range of voltage we are using in this? So somebody said 24, then 48, right? But they have jumped now. Like now, if you look at it, even they jump to multiples of 12. Okay, again, and they have crossed 100 also. Some range of vehicles. But if you look at the international level, they have jumped to 400 volt initially, and again they jump to 800 volt again. Okay, just imagine, you just imagine 800 volt DC architecture inside the vehicle. So how it is going to be like. So that's what is very important. So when you are going for a high voltage level, that's the reason you need the WBG now. And not only that, that high voltage, how fast you are going to switch is also another important point. That's why the switching frequency is also much more important. But there is a trade-off is there. For example, you can see the graph in the right side, inverter efficiency. So how fast you are switching, for example, 10K to 1 mega, you are switching frequency range. And if you look at the efficiency in the y-axis, so you can see that once you cross the 100K, so your efficiency is drastically going down. So that's another challenge. So you need to select the optimum operating frequency as well in order to maintain this efficiency good, and as well as you can reduce the losses as well. So there are some companies, for example, Porsche or Tesla, or if you look at it, Wolfspeed, okay, that is another standard they are using it. So they have a very good 800 volt architecture, and if you look at, they are using a different kind of WBG switching devices. So this is another good example. So how you can operate at 650 to 1200 volt, and how you can see the impact in the switching frequency versus efficiency. The next thing is about role on onboard chargers. So for example, this is the exact picture, whatever you can see, the size of the onboard chargers inside your vehicle. So you also have like SIC diodes, then GAN switches, fast acting switches. Then you also have inverters, GAN inverters. So you can see that after that, you can see a dual active bridge. So that is for the charging purpose. So you can see this is the kind of stages involved. So where you plug is in the input side. So you are seeing the AC supply and how you are going to charge your battery as well as how you are driving the motor. So this is also another important thing. Okay. So the conversion circuit, it is almost, it is kept inside your car itself, which is called onboard chargers. And if you look at it, GAN, actually you can go up to 22 kilowatt. Nowadays you can go up to 50 kilowatts also. So Infineon is a very good example. Okay, so the name is called CoolGAN. So the CoolGAN is a very good example from the Infineon, so which is having a 22 kilowatt fast charging technology. Why it is very important? Because if you look at it, the power density is also very high. That means 3 times the silicon-based system. So that is what we need it. I hope you might be knowing about the energy density versus the power density. So where you need the power density more and where you need the energy density more. The next thing is about DC to DC converters. So there also we need a very high switching frequency. Why? Because I don't want my DC to DC converter both sides should be big. So I want to make it very compact because everything you want to keep it inside your car, right? So I want to make it as a very compact size. So this is just one example you can see. This is the size of your DC to DC converter based on GA. Okay. And you're supposed to achieve 98% efficiency. And this is one of the model number also they given like a GS6 10080. So this is a one model which is commonly used in this WBG DC to DC converter. So one important function of this is nothing but why we need DC to DC converter inside your car, because I want to manage the voltage level for your auxiliary system. So that is another challenge because you need a different voltage levels, right, inside your car. So that is also there. Also, you can just use this WBG based devices. The next thing is about the industry product and specifications. So what are the industry products available in the market? For example, you can see what is a DC to DC converter available. So we have seen GAN GS6 10080. And we have seen Infineon CoolGAN, which is operating at 400 volt. And there is another thing called Wolfspeed. This is a kind of inverter which is operating at 1200 volt. So these are the some good examples which is having a lower losses, then which is having a higher efficiency, which can operate at a high power rating because I need to charge my vehicle, battery vehicle very quickly. Okay, so fast charging. So that is another thing. And another important thing is I can operate this converters with a very high switching frequency. So in terms of megahertz. So this is also one of the important reasons. So why we need to jump to a GAN devices or SIC devices. So what is the market trend now? So far I have said like why Mahindra or Tesla, they want to increase the range, and why they want in the market, they want to go for this higher range. It's purely because they want to operate in 800 volt platform. Fast charging is demanding this. Okay. So if you look at it, so you can see the graph. So what is required? That means the semiconductor devices market starting from your 2023 to 2033. Okay. So this is given in USD, billion US dollars. and they have marked this SiC, GAN, and then other material types also. If you look at it, for example, SiC and GAN is a keep on growing. You can see the market, and parallelly you can see how far it is growing. For example, we are now in 2025, and where we are, it's around 2.6. Okay. Now, if you look at 2030, it is around 4.5 is the thing, and projected one by 2033 is around $6.2 billion. And the market is growing at a range of 11.4%. So this is a forecasted market. So you can just imagine now, so how the market is growing now. Okay. So based on what? I supposed to explain this because 800 volt platform is very important nowadays, and there are a lot of research is also happening, and we also tied up with one of the industry from the US, and we are also submitted one project based on this 800 volt platform also. And you are welcome, suppose from DST or SCRB or ministry, if they given a call for, so we are ready to help for this 800 volt platform project proposal submission, if anybody is really interested. Okay, what is the challenge? Challenge is nothing but you are looking at the power electronics market size. Okay, power electronics market size is also, it's a keep on increasing, and you can see by 2028 it is 3 times than that of the 2023, and 2033 it is going to be 5 times. So, but the one thing is that the price. So what I want to say from this graph is, so when the market is growing and you have a more and more production, if you have a more and more production, so it is expected that the price may decrease. So that's what the positive sign here. Okay. And another challenge is, as of now, it is a costlier. Okay. 2 to 3 times it is a costlier than the silicon. Okay. Hope you might be knowing very well, right? In India and all, you can see they might be using low-cost alternatives, especially from China. They are not using the actual WBG devices in most of the applications. And second thing is about the complex process, because it is related to the wafer manufacturing. So hope you might be knowing about it. So this complex process also, it's going to be tougher. And it requires that particular climatic conditions or standard temperature conditions is required. So that is also another challenge, and the material also another thing, like you need to buy these materials. Okay, so how it is going to be tough for the battery materials, like for example, you need a mines, right? Because nowadays, if you look at the most of the mines are in the African region, and those mines and all, it is operated by Chinese operators only, or from the US operators. So just imagine. So this is another challenge. So whoever is having the mines, and they will be the dominating one in the future. So what is the another challenge is nothing but like packaging, then fabrication. So these are the two important things. Even though if you look at it, maybe you can mute.
Kindly mute yourself.
Okay,
Yes,
so
sir.
another innovation. Yeah. Can I continue now?
Yes, sir. Please proceed, sir.
Yeah. So another innovation is nothing but how we are going to do this packaging or thermal management, then fabrication. So many things are involved. Like, so you might be knowing about the government of India. They have already started the giving the focus on the semiconductor manufacturing. So this is another area so they can focus. For example, especially for the GAN devices, because this is also coming under the semiconductor device, but this is coming under the special category called WBG. So there is also considerable focus should be there, and policy should be changed in this particular case, like how we are going to manufacture, how we are going to package. So how the structure is going to be, how we are going to manage the thermal things like heat. So you can see the picture, right? So how they are assembling the PCB, then GAN FET devices. Then you can look at how they are going to arrange the space, okay, spaces. That means the surface mount devices. Then how they are arranging the heat sink. So many things are involved. And especially when you look at the fabrication, like 8-inch wafer fabrication, so you can see so how they are managing the power, then how they are managing the wiring. Okay, then base plate. So many things are involved. So the heat and the current should be equally balanced. So that's the main thing in this. Okay, so even though you have heat sinks are available, but this is another challenge. So how you are going to manage inside the fabrication. If you look at the different case studies, for example, so what we are talking about is the 800-volt technology, 350 kilowatt. So why we need 800-volt 350 kilowatt? Because I want a range, extended range. And if you look at clearly, so it also requires the like a WBG semiconductor devices. So whatever you are seeing in the right side, so that should be incorporated inside your car. That means your onboard charging. So if you take example like a Tesla, like a Model 3 or Model Y, they are using these SiC inverters. Actually, they are the first one to adopt this SiC inverters. And when you look at the Porsche, okay, Taycan model, they are also having the 800-volt SiC platform, which is for the 270 kilowatt charging. So what are the key advantages? Like I cannot say advantage, like a key constraints like a high insulation and clearance cost, low reliability and higher voltage pack. So these are the key constraints, and more series connection increase the failure impact. So because it has some series and parallel connection, so in order to meet out the voltage and the current, right, capability, so it has some failure analysis you need to do it. Lower voltage packs are more energy dense. That is a positive point. Higher voltage system require more electrical clearance as well as a larger PMS. So I hope you might be knowing about the electrical clearance, right? Electrical clearance means you should have the spacing. Okay, so that is very much needed inside. And not only that, a human being is traveling inside the car. So that also you need to take into consideration. So when you are operating at high switching frequency, even though you might be watching in most of the YouTube videos, you are using your earphone and mobile itself. They are saying that
Sir, you're under mute, sir.
hello.
Yes, sir. Now you are audible, sir. Please go ahead, sir.
I don't know. Somebody muted. Okay. Actually, this is a drawback of online kind of webinar or online teaching.
Yes, sir.
If somebody is not pointing out, it is very difficult for me also. Okay. I don't know how it is muted. I really wondering. Okay. Future prospect, if you look at it, so globally, if you look at wide bandgap power semiconductor device market is expected to account for like in terms of million US dollars by 2028. So how we compare the different devices. So now if you look at this graph, we are comparing with the different countries, how it is going to be projected. Okay. If you look at North America, is also keep on increasing. Europe also, because they are the one they are actively implementing or incorporating it. Asia Pacific also, if you look at it, like countries like China and Taiwan, so many other countries, they are also jumping into this. South America, especially Brazil, they are the one they are doing this most of the things, and Middle East and Africa also keep on increasing, right, in their business market. So it has a very good business market for the next 3 years, 3 to 4 years. So this is going to be the impacting the entire EV charging market. So if you look at this recent semiconductor industry update, so there are a lot of things happening like full speed and ZF. You might be knowing ZF also is available in India. So they are the one manufacturing the 8-inch SiC fabrication in Germany. And Infineon, they have a Malaysia plant for this SiC and GAN. That's why I said in Asia Pacific also it's keep on growing, not only in the Europe. And what about India? India is also have a policy now, but Tata has also started, right? Tata Electronics company. So they were into this particular business with the tie-up from the Taiwan company. But I'm not sure like how fast this industry is growing in India, because which requires a lot of constraints, whatever we have seen in the previous slides. So I just want to finally summarize like what we discussed is like WBG and different bandgap devices, how its rating is going to make an impact. Why it is very much needed because of it enabling the lighter, faster, and more efficient electric vehicle. And what is the action to be in the future by the government or policymakers? Accelerate the R&D to lower the cost and scale the production. This is another important point we need to focus. This is which is not happening, especially in India. Just it started now. We are more focusing on this as well. Because even the US also, they already announced, the recent government, they announced they want more production units in US. They don't want to buy anything from the outside. So that is another impact in this EV charging domain and as well as the electric vehicle domain. As far as the EV is growing, then WBGs also will grow. That means there is a good opportunity for the different electrical engineers who is working on this power semiconductor devices. There is a good opportunity. So hereafter, you can say to your any of the meeting or any of the school students or whoever is asking about which branch they can select. I think you can blindly you can say that yes, electrical, electronics, and this circuit branch, definitely there is a good scope in the coming years. So you can without any hesitation you can say this. We should be proud of this. Thank you very much for the opportunity. So I have referred different kind of references for arranging this particular webinar, especially in this particular topic. It was very much interesting. I have referred these things and I referred some case studies also. I hope you might have enjoyed this presentation and you would have got some 10% of understanding of our
Thank you, sir. Thank you for your wonderful speech, sir. I request the participant, if you have any queries, you may post the same in the chat box, so our professor can answer you. Dear participants, if you have any queries, you can please post the same in the chat box.
Maybe it's 9 p.m. in India, right? So everybody might be hungry or in the sleeping mode.
Sir, there is a question, sir. Which converter is used for battery power management at this time?
Battery power management?
Yes, sir. Battery power management. Which converter can be used? That's what the question, sir.
Especially for battery management system, BMS, I think we need bidirectional or DAB, dual active bridge. So these are the two constantly used converters for the battery management system. Especially whenever you want to, for example, charge or discharge, something like that. So you need this. There are a couple of research papers is also available on bidirectional and dual active bridge.
Okay, sir. Addison, is there some more questions you can place post the same in chat box? Someone asking, sir, please share some EV charger based on WBG devices. Is there any EV charger? Such kind of ideas they are asking, sir.
Oh my God, I have shown the pictures also. I have shown the company also. It was in my slide itself.
Okay, sir.
I'm not sure, like they have constantly watching this.
Sir.
Yeah, this is one of the thing, Tesla, and this is from the one of the package unit, and this, yeah, these are the companies they are doing this. So if you look at DC to DC, you can go with this, or OBC, you can go with the Infineon, or you can go with inverter means Wolfspeed. Okay. And this is the one of the device which is from the DC to DC converter, especially from the GAN device, like Infineon, sorry, GAN. Then next thing is, this is the one of the things. So you can see the complete architecture. So in the background picture, this is nothing but the Infineon CoolGAN. You can find it from the Infineon website itself. So this is the one they are using it.
Okay, sir. Thank you, sir. Thank you so much for your wonderful presentation.
Sir,
and
sir, I have, sir,
yes,
sir, I have one question, sir.
sir. Please go.
Sir, recently, which type of algorithm is used mainly used for tracking the power point maximum power point tracking in solar, sir, for electric vehicle charging, sir? Which type of algorithm is recently used, sir?
Actually, when it comes to industry, whatever we are doing research, none of the algorithm they are using in the industry. Because none of the algorithm is validated.
Okay, sir. Okay, sir.
For
So
example,
recently,
for research purpose, you can show it is extracting the maximum power. But when it comes to the practical application, so there is no proof or evidence that this algorithm is doing best. So far, if you look at it, they are using the conventional devices only, converters only in most of the applications. Even if you take any solar company, so they are using this conventional things only. Maybe they might be using dual tracking systems. That's it. So other than that, they are not using this optimization or neural network or artificial intelligence. It's not so.
Okay, sir. I saw different types of papers using like for Firefly algorithm. So that I asked, sir. Okay, sir. Thank you, sir.
Yeah, for publication purpose, you can use that.
Okay, sir. Okay, thank you, sir.
Thank you, sir.
Question about e-vehicle, sir.
Yeah.
So nowadays in India, BS6 model is using. And this BX6 model, if you using e-vehicle, mean how we can transfer the malfunction data through cloud computing? Is there any advanced technologies there?
Oh, I'm not sure about this question because I'm not sure about this BS6. Maybe I may need to go through this BS6. What is BS6 and what kind of cloud storage they are using? I'm not sure about that.
Okay, so beyond BX6, if you e-vehicle, how we find the malfunctions and how can it is transferred to customer sites?
Even I'm also new to that because I'm purely the electrical, especially power electronics background. So I'm not into that software side. That is purely on software side.
Okay, sir. Okay, thank you.
Thank you, participant. I think it's time. Thank you. Thank you so much, sir. Thank you, Umashankar, sir, for your nice presentation. You have delivered us a very delightful one, and we are very happy you are joining your hands with us in our ATAL FTP along with the Department of EEE of the Dr. Mahalingam College of Engineering Technology. And special thanks for you, sir, for being with us, sir. Thank you very much, sir.
Thank you so much. I am many times I am associated with the Mahalingam College. Even I visited last time. I think not last time, 2 years back. Yeah.
Yes, sir. Yes, sir.
Thank you. So see you all of you and have a great dinner and good night.
Thank you, sir. Thank you, sir. You may leave, sir. Participants, the FTP is about to close now. The chat box will be having the feedback. You can post it within 5 minutes. 5 minutes we'll be providing for the feedback to be filled. So kindly finish it off. Right now, our organizer will post the feedback once again. Kindly check for the feedback and you may fill it as early as possible.
Hello, sir. Hello.
Yes, sir. Yes, sir.
Not so in chat box in. So put this WhatsApp group.
No, sir. We'll not be posting it in the WhatsApp group. If someone is posting in the WhatsApp group, I think our organizer may close it out. So please don't post. Participant, I request you not to post the thing in the WhatsApp group. It will be available only in the chat box.
But I don't show in chat box in my.
Sir, see, our organizer has been showing you the way how you can open the chat box. Please see over there, sir. The screen now is telecasting to you.
Excuse me, sir. Hello.
Yes,
Sir,
how
will
can I
you
help
share
you?
these to us or not?
We'll be sharing you all the materials, sir. Don't worry.
Okay, fine, sir. Thank you.
Thank you. Sir? Yes, sir.
Yes, sir. FDP schedule will be sir or not, sir?
Sir,
SPP
we'll be
schedule is
sharing you. We'll be sharing you. We'll
already
be sharing.
emailed. Sir. We have already mailed all those things. You may see the same thing in your email as well as in the WhatsApp group. Day-to-day events have been shared. Don't worry, sir.
Okay, sir. Okay. Thank you so much, sir.
Sir, the link will be open for the next 5 minutes. You can just do it. I hope everyone is able to see the link. I have shared my screen too.
Can we leave, sir? Can we leave, sir?
Yes, sir. Yes, sir. If you have completed the feedback, you can just leave, sir.
Thank you.